Well, thank you very much, Srini, for your very warm introduction, and thank you, Rajesh, for tolerating astronomers. Again, we had one of your first meetings in your new site was on jets, as we just heard about from Ramesh, and it was a great meeting, and it had made a big influence on me there. So thank you for tolerating all these astronomers. I was going to talk about high-energy astrophysics because it's the most rapidly moving field at the moment, perhaps. But I felt sorry for cosmology, which seemed to be given short shrift in this meeting, so I was going to try out something that is a work in progress here. And I'm going to take a slightly sort of anti-physical approach to this to start off with, but I'm going to bring it back to physics at the end. So what I'm really going to talk about is the universe at large and looked at with the coarsest scale. And most of the activity in cosmology recently has been directed towards making global models of the universe and also to see it as a place where you can test ideas about fundamental physics. And the bottom line is very simple models of the physics and of the universe at large suffice to explain more and more of the data. And it's just like what's been going on in particle physics. There's an army of physicists and astrophysicists and astronomers going out there trying to break it, trying to break cosmology. And by and large, they're failing, just like they have done to break the standard model of cosmic physics. It's not because they're not ultimately destructive. It's the way to find new things. And here's just one example. This is the Planck data from the microwave background. It doesn't really matter what's plotted here, but it is in fact a cross-correlation of the temperature and polarization fluctuations as a function of spherical harmonic. But this is a 6-parameter model, basically, and the graph after graph after graph, it fits. So this is the impressive thing, and it works. Now, what I'm trying to do is something so much cruder. It's on a totally different scale. I'm trying to make, with my colleagues, Lawrence Perovassa and Phil Marshall, I'm trying to make a very crude model of the universe at large. And this is what Columbus used to persuade the monarchs in Spain to let him go. And something not even that good is what we're after here. And it's the first step along something. And so I'd just like to tell you a little bit about that. I should perhaps say that this is work I've been trying to do this for a few time, but it was intermittent because there were a couple of births that happened. My principal collaborator, Laurence, had a baby, and then I, with my colleague Kip Thorne, finished off a textbook around about the same time. They weigh about the same, but there is a crucial difference here. The baby actually grows, it's doubled in weight, communicates, eats, feeds, does all the good things. This just sits there. I sing to it, I feed it, nothing happens. It's just, I think this is a problem in computer science, but somebody can explain it to me. Anyway, all right, enough excuses. All right, here's the famous Planck picture of the microwave background. What you're seeing is 10 parts per million fluctuations in the temperature just plotted out on the whole sky. And I'm going to use the crudest version of this. I'm going to degrade this data horribly, and it's been used and used and used and used in brilliant ways, but I'm going to try and use it in a very primitive way. Now, just to make it a little bit clearer what's coming along, the projection that they use, which I think people figure it out, this is the whole sky seen, but put up what's called a Wadia projection. Lines of latitude are horizontal lines here. These are X, Y, and Z. And so that point there maps onto that point there, that maps onto that point there, and so on. So you've got the whole sky around you, put it onto a plane. And this is the one that's convenient to use for these purposes. So there's the Planck microwave background. Now let's talk about the way I will think about cosmology in this unit. And I emphasize again, I'm only using the simplest version of cosmology which appears to suffice. And if it turns out that future observations show us something richer, then that's great and it can be accommodated. So what I want you to think about is the universe is expanding, and I want to think about the universe today. So every observer on distant parts of the universe measuring the same time since the Big Bang. That's not what we see. We see on our past light cone when the universe was smaller. But just imagine the universe today, and we can perform this experiment after the fact, or future generations will see it, or whatever. But so if you think about it that way, then basically what we have is a series of spheres, and I've just shown circles here. There's the Big Bang itself, which is where the radiation that comes from, that we see today, that comes from the earliest times, and it's just inside that is a sphere that we call the epoch of recombination, and this is when hydrogen goes from a plasma to atoms, and 95% of the microwave background that we see, which has told us over half of what we know about the universe, comes directly from that surface. Okay, for our purposes, that means all of it. As we go into smaller spheres, remember this is the universe today, not as we're seeing on our past light cone, then there will be a fuzzy region around here when the universe gets reionized. These are the first stars and galaxies. This may be where the LIGO black holes are formed. It's one of the things that David mentioned. And then if we look inside that, this is where the first real big galaxies are formed, where we see most of the galaxy formation. This is in this sphere here, and these are labeled by the times and the scale factor. The scale factor is just the size of the universe when we were looking at it, when we're looking down our past light cone, relative to the size today. So that's a measure, if you like, of size. It's also a measure of time. And then if we go to comparatively recently, this is when the famous acceleration of the universe caused by most of what's in the universe now, which people call dark energy, but I will, the simplest version of this is just the cosmological constant, as Einstein said. There's no evidence it's anything other than that, and most of us, many of us who, with a sort of a classical relativity background, expected this. The dark energy only takes over comparatively recent times. So we're looking, when we look at the microwave background, we're looking inside this sphere, and the job is to try and understand the grossest structure within that sphere, within what we can see. And then here I've got a particular, how do we go? Yeah, here I've got a particular wave. I'm going to obviously do Fourier analysis here. I've got a particular wave, and that wave, in this case, has a wavelength of 6 gigaparsecs. So this is enormous scale. And it's waves like this that I'm thinking about, and my colleagues as well. The point I must make is that on this very simple model, we can evolve the universe. So if anything we can see on our past light cone, we can then project forward and backwards in time. The physics is quite deterministic. These are the famous Friedmann equations that are used. You need GR to derive them, but it's really quite simple. You have to just know what the density and pressure are, and there was even a book written about it, but never mind about that. Okay. Okay, so let's move on. So that was a sphere. Now let's talk about the music, and obviously there's a nod here to Kepler and Pythagoras and so on. The perturbations, which are introduced, are just very small perturbations at the dawn of time, and I'm going to emphasize the expression of them as essentially Newtonian potential. Now, more technically, it's just a perturbation to the metric in relativity in a specific gauge, but we just think about it as Newtonian potential. And from that, by taking the second derivatives, we can get the density fluctuation, the velocity, and so on. And these perturbations, these are the perturbations that make the structure really just sound waves. They've got a little bit of gravity in there, and there's a bit of damping in there, but otherwise that's all they are. And important for our purposes, the long wavelength waves that I'm concerned about here are linear, quite linear. So this is an example where you can do linear physics, and that's why this has been a very successful activity for most of the time. And so what we'll do is just make a simple spatial Fourier transform of the potential, and you can get the densities and velocities if you want out of this, but just think about it as gravitational potential, and just expand in a series of modes in a box. So I'm just going to make a box, obviously bigger than the universe that we can see, and there's assumptions in that, and then just make simple Fourier expansion like that. And now, you could say, well, what the job we're really trying to do is to use this well-mapped temperature fluctuations on the epoch of recombination on the surface of the sphere, on the inner surface of the sphere. The thing that we can tell is that from those temperature fluctuations in this regime, to a good approximation, that tells us directly the potential. It's basically just the gravitational redshift one is looking at here. So we get the temperature fluctuations tell you directly the potential on these large scales. So that's just measures phi. Now, one of the things that was conjectured by Ted Harrison a long time ago, who was one of my contemporaries when Srini and I were in Cambridge, and it was a very bold conjecture, and it was put on much more solid ground by Zeldovich and Peebles and others afterwards, was that basically the initial fluctuation spectrum would be essentially flat in power. This is a bit like, this is where the music comes from. If you make a power spectrum of music, which you get probably from a Fourier transform, then it's basically 1 over f noise. So all music, like the beautiful music we heard last night, is all 1 over f noise, at least to a cosmologist. To the rest of us, we know there are phase relationships, their modulations, and all of that, which distinguishes music. But what was found that at least statistically was conjectured and appears to be the case is the Gaussian random processes, Gaussian distribution of amplitudes at initial times. It's going to evolve deterministically after that. But initially it starts off like that. And so that's what I like to say, that the universe began with a hum, not a fanfare. So it's the opposite of music. Okay, so what we're trying to do is something that there's a lot of resonances with words that have come here. The only thing that's going to distinguish what I'm doing from what many of the excellent discussions we've heard here in these words is what I think I've heard has been sophisticated science done, explained in a very simple way, and it's been great, and I've really thoroughly enjoyed it. This is very simple things explained, probably in a complicated way, but it's very simple things is what I'm trying to emphasize here. So we're doing something that you would abuse, as some of us, as I will do here, the word holography, which does actually technically mean something slightly different, but there's just this idea of going from a 2D surface to get the 3D interior. And what we want to do is reconstruct the interior potential within the sphere, and then we can get everything else we need to know, the density and the velocity and all of that. So what we've got is the potential defined on the surface, and we can expand that in the usual way in spherical harmonics. I'm just going to label those as Y, a spherical harmonic. I'll just call it Y. That means indices L and M for most of us. And there's a coefficient here, A. So we just need to get those coefficients A there. And one of the ways you can do this, I haven't really got time to show all of this, is you can treat L as a continuous variable by just adding up the next round of spherical harmonics and so on. And I'm just only going to go to about L of 8 or so here. We have ambitions to go beyond that. So we're looking at very low scale structure. So as we go from L equals 2, say, we throw away the dipole and the monopole, we go to L equals 2, and then go up to L is 4.5, you're making a continuous variable, and then up to L is 8. You see more and more structure coming in. Now, so what we do is then we know, if we know what the interior set of Fourier modes are, and these Fourier modes are the ones that we have a conjecture that seems to be satisfied by data, that they're Gaussian random field, then we've got a simple matrix that will take them into the coefficients on the sphere, and the job then is to invert this equation. It's very simple, of course, expressed like this way in the presence of noise and a lot of other complications. And basically, the bottom line is you do a Bayesian reconstruction, and it works pretty straightforwardly up to a L of about 8, and then beyond that, we've developed some techniques to take you beyond that. And then what we want to do is to just recover a smooth map in terms of potential initially of the interior of this sphere. So we're just looking for a smooth map, not a little structure and so on, which is the subject of most of the analyses of the microwave background. So you obviously do this with test data and noise, and you go through various exercises to try and optimize the choices in this. And for the goodness of fit, the simple thing to do is just to see how well you reproduce the potential, the RMS fluctuations, and so on. There's actually another way of doing this that I'll say a tiny bit about because it relates to trees, which we had a lovely talk about this morning. And this is a sort of non-parametric approach. And I'm going to just describe it initially just in 2D. Just look at the microwave background that you have, and then draw the separatrices. These are the contours of potential, or equivalently temperature, that pass through saddle points. Okay? So the highs and lows here, and you pass through saddle points. That's the next saddle point there. And then as you increase the resolution on the sphere by increasing L continuously, so you build up saddle points, more and more maxima and minima and so on. And you can represent this here by essentially a very simple tree. I've just drawn the equivalent one here. And you can do this with, obviously, with the real data, and more interestingly, with test data, just to see what's going on. And there are, in fact, tests of Gaussianity that I think are a bit different in this. And I was particularly excited by the things I was listening to this morning, because obviously I've tried to read what I can, but I think there are people here who could teach me an awful lot. That's why I'm talking about this, actually. And there's obviously two types of contour here, what I call the lemniscates and limicons off of the famous classical curves. And there are various little statistics you can do that random fields should satisfy, I think. And so there's tests in here, I believe. But let's just move on. But I did this in 2D here because it's easier to visualize. But if you just think about it for a moment, the same thing happens with 3D. The nesting of equipotential surfaces within this sphere also defines a tree and in a very similar way. And the statistics of that, if you've got all lemniscates in the northern hemisphere and limicons in the southern hemisphere, you know that would be a terribly non-random process. So that's very much a work in progress. We haven't got too far along that. What we have done is done some test reconstructions using trial data satisfying the sort of Harrison spectrum. So here's the signal, here's signal plus noise, here's the reconstruction. Not very ambitious, as you can see. This is the box, if you like, and you can vary the size of the box. And this is the blue thing here is a sphere, or certainly projection here. And you can do a roughly good job of reproducing using this technique, inversion, as long as you're not too ambitious about getting too much small-scale structure. So if we take the Planck data, we can do the same again. This is just doing a very simple-minded approach with observation, the reconstruction. The residual that we get looks like that, and this is one representation of it. I've got some movies of this, but it'll take too long to show them. And then that's the sphere inside the box, and we vary the size of the box and all of that. And then if we do a slightly more sophisticated approach involving marginalization over the large K modes rather than smoothing them directly, then we get something like this. And this is taking sections, the lines of latitude in that mole-wider projection, if you like. And ultimately, when we're a bit more confident we know what we're doing, we're going to make 3D printing of these, which you can do in the local store nowadays. Okay, so I'd like to take Robert's title, which came from Abraham Flexner, I believe, at the Institute for Advanced Study, and sort of turn it on its head. I mean, it was intended to say why what we do at the Institute of Advanced Study is good for the rest of you, but this is slightly the other way around. This is what I'm trying to do here is good for people who work at the Institute for Advanced Study, who are much more concerned about the physics and the fundamentals and so on. Because what I'm been describing is something that is the sort of activity of, I'm proud to be an astronomer, the world's second oldest, not largest, second oldest profession, and I'm proud to be that. And but you know, traditionally what we've done is sort of sat on our backs on the hillside and made up stories about what we see in the sky, and that we're still doing that. So I've been describing geography in some sense here. I've just been just saying what it looks like. And so that, from the point of view of a theoretical physicist, is useless knowledge. But I'm trying to say it might be a little bit useful. So one of the things it can do is it provides priors for the giant surveys like LSST and so on that are coming, and many other ones that'll tell you things like if you believe in something other than the cosmological constant, you can set limits on neutrino masses, tests of GR, and so on and so forth. So there's a lot going on there. But the second thing it can do is it can, I think, Lawrence and I, in particular Lawrence has put quite a bit of effort into this, be a probe of inflation, which was, for those of you who don't know, was a theory proposed in the 1980s, which rationalized some very big puzzles. It's a very bold theory, especially those concerned with causality and defects and so on. And subsequent observations appear to be consistent with the simplest viable version of this. And that's a very non-trivial statement observationally. It doesn't mean it's proven beyond all doubt, but it's the best theory we have, and what the simplest version of it is compatible with the observations as we have them, and they're still coming in, of course. So the link to inflation, I mean, the key point here for those who know a bit more about it is essentially the phase. there's two things you can do with this. If we can reconstruct the actual modes that describe the miserable universe we actually inhabit, rather than some statistical ensemble of universes, if you can actually get those modes, then you can see whether there's enough of them there. You can see whether phases are random. That doesn't come out of the normal power spectrum approaches and so on. And you can also get the slow roll parameters, for those who knows what those are, for this particular range of k-space and so on. And that's again is work in progress, but I think we're now both working seriously on this, and so we have to get back. So this part of it, since it's a long-term program, what I did first of all was to use a very restricted input data set, which is just the CMB, nothing else. We put in polarization, can be put in. It won't help us very much here, and that's basically what we're doing. But then the next thing to do is astronomers with many surveys know a lot more about what's inside the sphere. They have surveys looking at quasars, looking at galaxies, and so on. It's a partial information, but it exists and it's already there. And incorporating this in some great big Bayesian stew is the task that we'll be next engaged in. And there's various effects associated with lensing of the CMB, the so-called intermediate Sachs-Wolf, baryon acoustic oscillations, and all these sort of things. And so we can use all these different approaches to doing measurement in the universe, and if we use the priors from knowing whether you're in a potential minimum or a potential maximum, that will help. Locally, we seem to be in a bit of a saddle, according to our inference so far. This is obviously going to involve machine learning. Sorry, that's right. And I know this not because I'm an enthusiast myself, but my two collaborators are writing papers as we speak on machine learning and applying it to different data sets. So we're going there anyway. But I'm with my enthusiasm because this is a system that's set up, I think, ideally for that. Next, third stage is to go to future data sets. The so-called epoch of reionization is a terribly challenging observation using hydrogen line measurements, and if they can pull this off, then we will have intermediate information about the structure of the universe halfway between here and recombination in some sense, and then these big survey telescopes of the future and so on. And then finally, I think there's an interesting philosophical question here of asking just, some very asymptotic distant future, what is knowable in principle? You can obviously go some way beyond the Big Bang, but not much more. And again, I won't say any more about that. So this is the summary. It appears to be possible to make very low-grade maps, just to start, and it can be made better, I think, with existing and imminent observational data. And there is some hope, at least in our thinking, that they will make improved tests of the standard cosmological model and measurements of it, and also yet another probe and test, perhaps, of inflation. Thank you very much indeed.
Other questions? Ramesh?
So, Roger, that was a very interesting idea, trying to extend the information from, let us say, the CMB down towards us.
Yes.
Naively, I would have thought that if I have some information on some wavelength lambda on that sphere, I can only propagate it about lambda in before I lose predictive power. Is there something that allows, can you actually use it to come all the way down to us?
You can, because the thing that you're throwing in, if you're putting no other prior, then you can do anything you want, joining up the contours. You can join them up in infinitely different ways. You can squash everything up to there. But if you put in the additional information, or additional assumption that it's a Gaussian random field, then in fact, you can get some way in. And it's the way that I know one going as k squared and the other's going as k cubed, but you can actually get some distance in. And the goal here is not
more
to get
than lambda.
Yes, oh yes.
Okay.
And it's basically you're connecting across. And one of the sort of measures of goodness of fit is, we've tried to implement this, is to do with this tree approach, where you're not trying to get it exactly right. It's more like Magellan and so on saw with the sphere. You knew there was South America over there and there was Africa over there and there were great big lumps there, but you didn't get the shapes right and you got it moved over quite a bit. And that would give you a poor goodness of fit, but this topological description is more what we're after, I think, in the first instance. And that's more robust than getting it exactly right there. So it's really the topology approach that I'm sort of more interested in right now. But just the other thing is that we've already tied our hands behind our back by only using the surface. The next stage is to throw in the interior, because that provides a great big peg for you in the middle. Yep.
This may be very naive, but shouldn't there be some compatibility with the large-scale structure that you observe from the galaxy surveys? And maybe
absolutely, and any optical cosmologist, here will be don't want to hear this, but in that first picture that I showed, the surveys don't go that far, so we know very well what's going on in our neighborhood. If you go to the sort of maps of the world from the 15th century, then whoever made that map, they've got rather detailed information on the coastline of England or Greece or whatever it was, and then it's very vague when it gets out to China and so on, although the Chinese would do something inverse from that. And so so we know very well a lot of structure, things like the Great Attractor and so on. We know structure in our local universe, but on the scale of, say, 3 or 4 gigaparsecs, we just know one point, essentially. But the surveys are going deeper, and if the epoch of reionization investigations actually work, and they've got to get a tiny signal out of an enormous galactic foreground, it's terrifying to me, but they think they can do it, then we will have really good information at just the right place.